Hello, this video is about theoretical and experimental probability. And in it, we're going to find the theoretical probability of an event, as well as find the experimental probability of an event. So, we're going to cover a lot of vocabulary. We're going to talk about all these things. So let's go ahead and get started by talking about them within this example. What is the probability of rolling an even number? Well, probability is the measure of how likely an event is to occur. So what I'm really asking you here is, how likely is it that I roll an even number? Each possible result of a probability experiment or situation is an outcome. So each possible outcome, and like rolling a 1, that's an outcome. The sample space is a set of all possible outcomes. So for this example, the possible outcomes are 1, 2, 3, 4, 5, or 6. An event is an outcome or a set of outcomes. The event that I'm talking about here is having an even number. That's the event I was interested in. And so we have an experiment or situation such as rolling a dice or spinning a spinner, but it could be anything like picking something from a bag or I don't know, choosing a door. It could be anything for the experiment there. Now, probabilities are written as fractions or decimals, and they range from 0 to 1, or as percents from 0% to 100%. So we don't have negatives and we don't have anything really above 100%. Either it's 0, impossible, that would be like a 0, or if it's for sure certain, that would be 100% possibility, or 1. If it's as likely to happen as not happen, then we would say a 50% probability, or 0.5. So, equally likely outcomes have the same chance of occurring. When you toss a fair coin, heads and tails are equally likely outcomes. Or, when I roll this dice, rolling a 1 and rolling a 2 are equally likely outcomes. Favorable outcomes are outcomes in a specific event. For equally likely outcomes, the theoretical probability of an event is the ratio of the number of favorable outcomes to the total number of outcomes. So, if we're trying to find the theoretical probability, we would find the number of favorable outcomes that we want and put that over the total number of outcomes in the sample space. So let's look at an example of finding the theoretical probability. Each letter of the word probable is written on a separate card. The cards are placed face down and mixed up. What is the probability that a randomly selected card has a consonant? Okay, so we look at the word probable, and we can see that there are 8 possible outcomes because there are 8 letters in the word, P-R-O-B-A-B-L-E, and 5 favorable outcomes. The outcome that we want is a consonant. So how many consonants? We count the P, the R, both B's, and the L. So that's 5 of them. Now, to find the theoretical probability, we just divide the favorable over the total, 5 over 8, and we get our probability of 62.5%. 2 number cubes are rolled. What is the probability that the difference between the 2 cubes is a 4? Well, first of all, there are 36 possible outcomes, and I've put the outcomes right here in this picture. Either you roll a 1 and a 1, or a 2 and a 1, or a 3 and a 1, or a 4 and a 1, or a 3 and a 3, or a 5 and a 5, a 6 and a 4. So I've listed all the outcomes here, and there's 36 of them. Now, the probability that the difference is 4, we're going to have to find the number of outcomes that have a difference of 4, and then we're going to divide that by 36, because there's 36 choices. So there are 4 outcomes here that have a difference of 4, a 6 and a 2, a 5 and a 1, and the dice could also be the other way around, a 1 and a 5 or a 2 and a 6. All right, so the difference between those, 4 would give us 4. So that means the probability that the difference is 4 is equal to 4 over 36, which reduces to 1/9. The sum of all probabilities in a sample space is 1. The complement of an event, E, is the set of all outcomes in the sample space that are not in E. So the complement is the things that are not in the set. And if we want to find the things that are not in event E, we can take the whole set, which is 1, and subtract the things that are in the set. 1 minus E, 1 minus the probability of E, gives us the complement. Let's practice using the complement. There are 25 students in study hall. The table shows the number of students who are studying a foreign language. What is the probability that a randomly selected student is not studying a foreign language? Okay. Well, in order to find the number of students not studying the language, I can start with the students who are studying the language and subtract. Okay, so I can use the complement. The probability of them not studying the foreign language equals 1 minus the probability that they are. So what is the probability that they are studying a foreign language? Well, going back to the table from the previous slide and adding up how many students are there, we can see that there are 21 students studying a foreign language. That means the probability of not studying a foreign language is 1 minus 21 over 25, which gives us 4 left who are not studying, so 4 out of 25, or 16%. There is a 16% chance that the selected student is not studying a foreign language. Geometric probability is a form of theoretical probability determined by the ratio of lengths, areas, or volumes. So we can do the same thing with part over whole for pictures. Okay, a figure is created by placing a rectangle inside a triangle inside a square as shown. Okay, here's the square on the outside, we have the triangle inside that, and inside that we have the rectangle. If a point inside the figure is chosen at random, what is the probability that the point is inside the shaded region? So we want to find the probability of it just landing inside the shaded region here. In order to do that, we need to find the ratio of the shaded region to the area of the entire square, of the whole thing. So we're going to have to find the area of each of the pieces one at a time. We'll have to find the area of the whole square, that's side times side. We'll have to find the area of the triangle to be 1/2 base times height, and also the area of the rectangle inside here, length times width. So first let's find the area of the entire square. The total area of the square is 9, each side is 9, so 9 times 9. The area of the square is 81. Okay, so that's the whole big thing we're dealing with. Next, let's find the area of the triangle. Well, the area of a triangle is 1/2 base times height, and it looks like the base going all the way across the triangle here would be 3 plus 3 plus 3, 9. Okay, the base is 9, and the height of the triangle is the same as the height listed on the side here, 9. So the area of a triangle is 1/2 9 times 9, which gives us 40.5. Next, we can find the area of the rectangle. The rectangle on the inside here is length times width, and that's going to give us 3 times 4 for the rectangle. So now we can find the area of the shaded region by subtracting. So we can say that the triangle minus the rectangle in the inside of it will give us the shaded region. So if I subtract these two numbers, 40.5 and 12, I can find just the area of the shaded region to be 28.5. So now I can answer the question. The probability is going to be my ratio of the shaded area to the total area. So if I divide 28.5, which was my shaded region, over 81, which was my entire square, I can find the probability of the shaded region to be 0.35 or 35%. So great. You can approximate the probability of an event by using data or by experiment. For example, if a doctor states that an operation has an 80% probability of success, 80% is an estimate of probability that's based on similar case histories. Okay, so each repetition of an experiment is called a trial. The sample space of an experiment is the set of all possible outcomes. The experimental probability of an event is the ratio of the number of times that event occurs, which is the frequency, to the number of trials. So experimental probability is found in the same kind of way that theoretical probability is. The number of times the event occurs over the total number of trials. Experimental probability is often used to make estimates, used to estimate theoretical probability and to make predictions. So, here's an example. The table shows the results of a spinner experiment. Find the experimental probability. Now, before we find that, let me just state here, the experimental probability is different than the theoretical probability because we don't know what the spinner looked like. If we could look at the spinner, we would know, we could look at the spinner itself to determine what the exact probability is of rolling a 4. But since we can't look at it, we can only look at the outcomes that are happening. And each of these events is an experiment. So that's the difference between having experimental probability versus the theoretical probability. So the outcome of 4 occurs 14 times. And if we add up all the occurrences here, it adds to 50. So to find the probability of a 4, we're just going to divide 14 over 50, which gives us 28% for our probability. What about spinning a number greater than 2? Well, a number that's greater than 2 would have to be a 3 or a 4. There are 2 numbers to choose from. So we would have the 19 as well as the 14. We would need to add those together. And so 19 and 14 is 33 over the total of 50 gives us a probability of 66%. Okay, so in this lesson we learned that the probability is the measure of how likely an event is to occur. An outcome is each possible result. The sample space is the set of all outcomes. An event is one outcome or a set of outcomes. Equally likely outcomes have the same chance of occurring. Favorable outcomes are outcomes in a specified event. Theoretical probability is the ratio of favorable outcomes to the total number of outcomes. The complement are the things not in the event. Geometric probability is determined by the ratio of areas. A trial is a repetition of an experiment, and experimental probability is the ratio or frequency to the number of trials. All right, and that's the end of this video.